Section 4.1 is about maximum and minimum values, and this is a topic that is familiar to us because we have studied these in pre-calculus. Before we appreciated features of the graph, and we found the zeros, and we found the minimum and maximum values, and we talked about absolute and relative minimum and maximum values. Now we're going to give them a slightly different name, but it is the same idea. And not only that, but we're going to be able to find them ourselves rather than being given to us. Just a little bit of an agreement on the language. We're going to see differences between when we talk about largest value, when we talk about the lowest value, and whether we talk about it in absolute terms or if they happen around one area. So let's get started. We have here a graph on figure 1, and it says that this function in here is continuous, and you can see the domain between 1 and 7, and you can see the range between the values 2 to 5. Now this function increases, sorry about that, between 1 and 3, it's increasing, and then decreases between 3 and 6, and then it increases again between 6 and 7. And whenever you give that appreciation about increasing or decreasing, it's always talking about the x values. So where do you appreciate a high point or a large or the largest value on this function? And you can see that it happens right here. That happens to be the highest point. Even if we didn't have any coordinates, we know that that's the highest point. So where does it occur? You would say it occurs at x equals 3. And what is the maximum value? And your answer would be it is 5. Or you may say f of 3. But since you know that f of 3 is 5, then you will say 5. But if you didn't have any values in here, then you will say, well, it happens at x equals 3, and how much it is, whatever f of 3 is. So on the next slide, it is just saying the definition of absolute maximum and absolute minimum, and they talk about the domain of the function. So if it's the absolute maximum for the entire domain of the function, if it's a maximum value on the entire domain, it's called absolute. And the same for minimum. If it's the lowest one in the entire domain, then it's called absolute minimum. Another word for absolute is global. And whether you talk about a minimum or a maximum, either one of them is called extreme values. And it kind of does make sense. Extreme is at either point, even when it's the lowest one or when it's the highest one. Now in this figure, we see several low points right here, and right here. And then you can also see several high points, so this one, and this one as well. So there's going to be a difference between how high are the highest points or how low the lowest points are. So for example, if f has domain between a and e, actually I can just say if this is the entire function of f, then definitely this point right here is the lowest one occurring in the entire f. So this would be an absolute minimum. However, this low point here at c, it's a low point, but it's not the lowest on the entire graph. So this will be called a local minimum. And it happens to be the lowest point around the values x equals c. So if I'm only zooming in, I can't really do that right now, but if I'm only zooming in around these points, I can see that x equals c has a minimum, and that will be called local. In here, this one is the highest point on the entire graph, so this would be absolute maximum. This one would be a low point on my graph, not the lowest, but this is the lowest one around values x equals e, so this would be a local minimum as well. Now the definitions for local maximum and local minimum are here, and they only apply whenever x is near that point. So for example, 4 here, f of 4 is a local minimum for x's around 4. F of 8 here is a local maximum for all the x's that are around 8. And this one is a local and happens to be an absolute minimum as well, because it's not only the lowest points around 12, but it's also the lowest point of them all. So that's the difference between local and absolute. The absolute one is the one that occurs if you consider the function in its entire domain. Now for any function, you may or may not have local minimums and maximums, and you may or may not have local absolute maximums. So it depends on the function, and you have to look at it in a case-by-case basis. So for example, we have the function cosine of x, and I'm gonna remind you of the graph of this function. It looks like this, and you can see that it has several maximum points, several maxima. So for example, where do they occur? At negative 2 pi, at 0, at 2 pi. And if I can continue doing that, it happens at 4 pi, then the next maximum happens at 6 pi. And how much is the maximum, or what is the maximum? Well, the maximum is 1, and it happens whenever x is some even multiple of pi. Now let's look at the minimum value. The minimum value of this function is negative 1, and it occurs more than once. It occurs at pi, it occurs at 3 pi, 5 pi, 7 pi, 9 pi, and so on. So it seems that the odd number multiples of pi, that's where we have a minimum on the cosine, and the even multiples of pi, that's where we have a maximum. So let's go back to our slides, and it says we hit the maximum value infinitely many times, and you can see that this is, let me just remind you from pre-calculus, this is how we write even multiples of pi. The cosine of even multiples of pi is always 1, and this is the way we write odd numbers. So the cosine of odd number multiples of pi is negative 1. Now this theorem, you have to be very careful because it talks about a closed interval, and this is only true obviously for closed intervals. And if the interval is open at any end, maybe at the beginning or at the end, then this is definitely not true. So if f is continuous on a closed interval, then it says f has an absolute maximum value and an absolute minimum value for some numbers. Now we have no idea where these numbers are between a and b, and we haven't learned a way yet to find them. However, it is just it is assuring you the existence of such points. So we have several examples of different functions here over a closed interval, and you can see that there is always you're always able to find an absolute value and a minimum value. In here, the maximum is f of c, and it occurs at x equals c. In here, the absolute minimum would be f of d, and it happens at x equals d. And in here, you have an absolute maximum at c. In here, the minimum value is d, and it happens to be at the end, and that's something that it's okay. The end points of a graph may be the absolute maximum or minimum as well, because we're talking about a closed interval. If we were talking about other functions where the domain is from negative infinity to infinity, then there's no endpoints to begin with. So that's something that we're not going to need to check if we're talking about functions that have a domain all real numbers. Now it says, note that an extreme value can be taken more than once. So for example, in here, just the way it did for the cosine, the maximum value was taken more than once. It was taken infinitely many times. So let's look at these two figures, and just to reinforce the idea that that volume is true as long as you have a continuous function and a closed interval as domain. So you have f here is not continuous, therefore there is really no way to assure that there is a maximum value, for example, an absolute maximum. You want to say that 3 is the maximum value for this function, but it wouldn't be true, because in here we have an open circle, which means out of all the points that you see being part of the function f, this one is not part of f, and it is highlighted by having an open circle. So 3 is not the largest y value on this function. Now, would it be the number before 3? And you will be right, it will be sure. But what is the number before 3 that is a real number? You don't know if it's 2.9. Well, obviously it's not 2.9, because between 2.9 and 3 there's a bunch of numbers, so you can never actually find out how much that value is. So we cannot have what is the highest y on this function. This one happens to have an absolute minimum, but you know, that is just an occurrence. It doesn't mean that every discontinuous function happens to have an absolute minimum. That's not true. You may or may not see one, but if it's discontinuous, then there is nothing that we can be sure of. You cannot say there will be or there will not be. It will depend on the particular discontinuous function. Now over here we have we don't have a closed interval because it is open at 2. All the x's that happen to be part of this function are going to be used from 0 open to 2 open, and therefore in here we're not guaranteed to have an absolute maximum. This function, this is an asymptote, so it's going to continue growing and growing and growing, and the y values will grow. So you can never actually find a minimum. Okay, so you can read that. I don't know why I have this twice. Okay, next. All right, so what are the characteristics of maximum and minimum values? Well, for one thing, you have a maximum or a minimum, and the tangent line, for example, happens to be a horizontal one. So I can read your minds right now. I know you're thinking, oh, the derivative must be 0, and you will be partially correct, but that is not the only condition for having a minimum or a maximum, either for an absolute or a local level. So let's read Fermat's theorem. It says f has a local maximum or minimum at c, and if the derivative of f exists at c, then the derivative is 0. So notice how the theorem, it just says if there is a maximum or minimum, then and the derivative exists, then the derivative is 0. It doesn't work the other way around. It doesn't mean that whenever you have the derivative equals 0, you're talking about a maximum or a minimum, because that's not true. The converse of this theorem is not true. It only goes one way. So for example, if you have this function, you know that the derivative of 0 is 0. Not only that you can appreciate that on the graph, but if you take the actual derivative, which is 3x squared, this is 0 when x is 0. But f doesn't have to have a maximum or a minimum at that point. As you notice that there are higher points than this one to the right of 0, and there are lower points than that one to the left of 0. So definitely 0 is not even a local anything. It's nothing. So so the converse of that theorem is really not true. So and also the other thing that I want to show you here, the derivative does not exist, yet this is the absolute minimum of this function. So it is not a requirement to have derivative of 0 for the point to have a minimum, or to be a minimum or a maximum value. So it is here reassuring you the fact that whenever f prime of c is 0, it doesn't mean, or doesn't necessarily mean, that we're gonna encounter a minimum or a maximum. So we're gonna define what are critical numbers. Critical numbers of a function, it says, happens to be wherever you have a value in the domain of f, meaning an x value, for which the derivative is either 0 or the derivative may not exist. And then we can say that we have a local minimum or a maximum. If we have one, then that x is going to be a critical number of f. So all critical numbers are not going to end up being minimums or maximums, but definitely when we have a minimum or a maximum, then we have they happen at a critical number. So they happen at a number for which the derivative is 0, or it may not exist. So what it is that we're going to do with this information, we're going to be able to find maximum and minimum values for any functions that we're working with. We can have a function that represents cost per month of, I don't know, your house bills, or anything that we want to measure, blood pressure, cholesterol levels, anything that you imagine. We're going to be able to find maximum and minimum values. Sometimes the maximum would be relevant if you're talking about maximizing profit or maximizing your grades, and minimum sometimes is more relevant when you're trying to minimize costs, or you're trying to minimize friction, because that gives you loss of energy, or trying to minimize I don't know, sweat. So there are some things that are positives that we want to maximize, and there are some things that are negative that we want to minimize. So in that case, we are going to find all the critical numbers, or all the critical values for f. That means we have to recognize whenever f prime is 0 or does not exist. We have to find the values of f at those points, and then we're going to compare them. We're going to say which one is the largest and which one is the smallest, and for those are going to be called absolute maximum or absolute minimum. And notice how we're working with a closed interval. We're not talking about an open interval.